Hello everyone, today we will continue our discussion on the physical layer and we'll talk about signaling. So here essentially the task is that given a set of bits of information, we have to convert them into signals to be sent either wirelessly or on a wire. And the question is how to do this given all the practical issues that we might have to face. So first let's talk about wired networks. So in a wired network we have less interference and less multipath and things like that, like we see in wireless networks. So things are a little bit more straightforward. And the term used for this signaling here is called line coding. So in the wireless case, the researchers use the term modulation. And we'll see why they use that term. So line coding is about converting a set of bits into some electrical signal that you want to send on a wire, electrical or optical signal. So let's think what would be the most straightforward thing to do, and we've discussed that already. It's called non-return to zero. Which is a funny name. I mean, they should have used something more straightforward. But what we do over here is that let's say that you have a 0 and a 1, right? Or 0 and so on. These are your bits. And we have to come up with some signal in order to signal what the bit is, right? So let's say this is a bit period. This corresponds to the first 0, 1 and 0 and so on, right? And what we've seen earlier is why not just have, let's say, minus 5 volts, let's say. Okay, whatever reference, it doesn't have to be minus 5 volts, but some fixed negative voltage, and for a 1 we go to plus, right? So very straightforward, the simplest thing you can think of. In fact, we just have two voltage levels. And let's say the positive voltage plus 5 corresponds to 1 and minus 5 corresponds to 0. So what are the issues with this? Okay, and let me go on to the... So what are the issues with NRZ? There are a couple of major issues. So one is clock recovery. So let's think about it. Why is this an issue? So we have 0, 1, 0, 0 and so on, right? Okay, so this is at the sender, and he's sending out some signal like this, right? Now the receiver is getting this signal and he needs to figure out where a 0 sent and when a 1 sent, right? And let's think about it over here. So how is he going to do it? So suppose I tell you that this is 1 second, just as an example. In 1 second is a lot of time. In practice, it would be very small, like microseconds or less than that. Okay, so suppose you are at the receiver. This is what the sender is sending out. How are you going to figure out whether it's a 0 or a 1? So you have your own, maybe you have your own clock. On your own machine, and maybe you sample the signal appropriately, right? So let's just say that the receiver clock, and maybe the receiver is sampling it, and let's see, he says samples it, he sees whether it's -5 here, then he says it's a 0, right? And if it's a 1 here, if it's +5, he says it's a 1. Suppose I'm doing it this way, right? And I sample again. I sample, right? So every 1 second I'm supposed to sample the signals. Okay? So that's sort of a simple way of doing it. Now it can happen that the receiver clock is a little bit, let's say, faster. It could be also the other way. It could be slower than the sender's clock. So it may be faster or slower. So why would that be in practice? I mean, so you have two clocks. Well, the thing is that there's no perfect clock that we have on machines. They are all imperfect. So you think that the clock is, let's say, 10 megahertz clock or whatever, right? Or it may be much higher, a gigahertz clock. But it's not exactly a gigahertz clock, right? There is some imperfection. So clocks, in fact, will be a little bit off. They may be a little bit slower or faster than an ideal, let's say, atomic clock. And they also have drift. So we have to keep that in mind. So they may be slower or faster. And they also have drift. So clocks might get even more faster or slower with time. Okay, so you would expect that maybe a clock loses half a second a day. Okay, that's not unusual. Right? Half a second or 1 second a day or something like that. But sometimes maybe with the temperature change it might lose 2 seconds a day or 3 seconds a day. Right? So clocks are not ideal. So in this example that I'm showing you, I'm exaggerating it a little bit, and I'm saying that in this case he samples like this every 1 second, but the receiver's 1 second is a little bit smaller than the sender's 1 second. So he says there is a 0 here, 1 here, 0, 0, 0, 0, 1. And you see that here there is a problem. So he says there are 4 zeros when there are only 3 zeros. So this is a problem, and so the receiver should use the same clock that the sender is using. So clock recovery is a problem over here, because from the signal itself you can't recover the clock. When you have a large number of zeros or ones, I mean, how do you recover the clock? So here, when you have these transitions like this, it's giving you some information about the clock. But if the transitions are not regular, how do you recover the clock, right? When you have lots of zeros or ones together. Okay. So this is a problem, one of the problems with non-return to 0. It's hard to recover the clock. Because of which you may have the receiver using a slightly different clock, and he might see an extra bit, or one bit might be missing, okay, if he has a slower clock and so. There's another problem, it's called a baseline wander. So let's say you have let's say we're talking about the sender, and suppose you have an amplifier. So I don't expect you to understand details of amplifiers, okay? I don't expect you to get that would be taught, let's say, in an electronics course sometime, right? But you have an amplifier over here. Okay, let's say this is a typical symbol in an amplifier, and it may happen that this amplifier is imperfect. So when you're sending out a signal, let's say that this is actual 0 volts. Okay, so the signal might have a little bit of an offset. Instead of being exactly -5 and +5, it may be little bit like, let's say here it has a positive offset. Okay, so this is sort of the average of this signal. I'm calling this a DC offset. Okay, and so this signal is going off to the receiver, and it might get corrupted with noise. Let's say the receiver gets something like this, right? Let's say something like this. And the receiver has to figure out whether it's a 1 or a 0 by looking at this, right? And let's say that there is some attenuation also, the signal amplitude too has decreased, right? So he is comparing it to 0. So let's say he is comparing it over here to this, right? And it might happen that one of these bits that was actually 0 might actually go over here. Okay, I'm just exaggerating it. Okay, so just because of the noise, because the DC offset is anyway pushing the signal up, and the noise pushed it up a little bit more, and when this is actually a 0, he might sample it over here and think that it is a 1. So he thinks it's a 1 when it's actually a 0. Okay. So because of these DC offsets, it might unnecessarily give you more errors. As it is, you have to deal with noise, and maybe the noise, of course, we haven't discussed why it's there, but it could be coming from the external environment, but it could also be there in the electronics of the circuits itself. Okay, so the receiver has an electronic circuit which is itself generating noise. Okay, so you want to get rid of this DC offset. So what does the receiver do? So the receiver says, I want to get rid of this offset. So how to do that? Well, really, if you take an electronics or communications course, they will teach you there's something called a high pass filter. So what is a high pass filter? In the last class we talked about a low pass filter. Okay, so let me just maybe show that over here. So if you have a high pass filter, then if you send a frequency which has a very high frequency, and of course high and low depends on how relative to how you design this high pass filter. Right? You can say that I want only frequencies above 1 megahertz to get. Right? So this frequency is higher than 1 megahertz, it will go through more or less unperturbed. So there's very little perturbation, very little attenuation. But if I have a low frequency, something like this, it will get attenuated a lot, very little will get through. So this is just let's say that there is a low frequency like this. If this frequency is sent through, it gets attenuated. And for the low pass filter, it is the opposite. This low frequency will go through without any attenuation, but the higher frequency will get attenuated. Okay, so if you have the low frequency, it will get through unperturbed, but if you have a high frequency coming in here, it will get attenuated out. Okay, so the receiver is going to use a high pass filter so that it gets rid of this DC offset. The DC offset is not going to get through. Okay, so effectively what it hopes to do, what you want this circuit to do is it pushes this particular signal a little bit lower so that the DC offset goes and the average is actually 0. So that's the idea, that's what you want. But if you use NRZ, non-return to 0, what's going to happen is you see this thing called baseline wander. So let's say this is my signal. Let's say I have a long string of zeros. And then we have, let's say it goes back to 1. Now this is the signal that is being sent, and if you send it through a high pass filter, what's going to happen? So you can think of what's going to happen. So this signal sort of what's going to be received. So let's say that we ignore the attenuation. So let's say this is what is received. Okay, so this sort of transition is good. The receiver gets it fine. Okay, there's a little bit of noise, but what the high pass filter is going to do, it's going to get rid of this particular, it thinks that this is like a DC offset and it gets rid of it. Okay, so this is what we end up with. And then this shoots up, right? Over here we get something like this. And let's say that the signal continued, we got a few zeros and so on. So this is at the receiver. And of course, if you have lots of these transitions, it will go down a little after some time. Okay, so, but I want to focus over here on this. So the high pass filter has thought that this is like a DC offset and it pushed it up. Right, because it got rid of all low frequencies. So suddenly now when there was a transition, it went really up. Right, the received signal went up. This was fine because we had only ones over here. So it would detect these as ones, which is not a problem. Here the problem is that we had zeros, but the signal is still high. It could be above my 0 volts at the receiver. Right, so the receiver might think that this is 1 over here. It will think that all of these are ones. And here too there are issues that in case when you're looking at the signal over here, right, some of it might actually go above 0. So are these ones or not? Okay, so what we had is the DC offset was a problem, so we put a high pass filter, but then when you had a long string of zeros, the signal itself got pushed up thinking this was a DC offset, and when you tried to detect what bits were sent, you made a lot of errors because there was in fact a large push up of the signal. Okay, so the problem with NRZ is when you have long strings of zeros or ones, because that's like a DC signal, it doesn't let you recover the clock, and it also creates problems when you have this sort of a high pass filter. Okay, so what is the solution? So I need to mention what is RZ, return to 0. Okay, because really in reference to this you give a name, a very funny name to a very simple signaling scheme. So what is return to 0? Well, let's look at it this way. So I have 0, let's say, and a 1 over here. And let's say another 1 over here. In NRZ, I would have just gone like this. But in return to 0, I want to return to 0 every time in every bit. So in return to 0, I have this, and I go back to 0 in between, in the middle of the bit. Okay. And for 1, of course, I'm going to go up, but I return to 0 in the middle of the bit period. Okay, so I return to 0 here in the middle of every bit, and that's what gives it its name. Okay, so in relative to this, in non-return to 0, we don't return to 0, which is why it gets that name. Okay, so here you can see that because you are continuously changing the signal, you never have a constant DC value for a long string of bits. Even if you have lots of zeros and ones, you'll still have the signal changing all the time, which is a good thing. So one of the issues here is that you have 3 levels. Three voltage levels, and that could be a problem if you just want to have 2 voltage levels to do your detection, transmission and detection, then this is not. So what is used in practice in Ethernet technologies is something called Manchester coding. (802.3) IEEE. So what is 802.3? 802.3 is the standard used for Ethernet, which is very, very popular in our wired LANs. So what do we do over here? So remember that when you have a string of zeros, you don't want the signal to be constant, you want it to change quite fast so that we can do things like clock recovery. And if we have a high pass filter at the receiver, things shouldn't go haywire, signal shouldn't get pushed up or pushed down, as the case may be. So we start with the non-return to 0. say that this is my signal. Let's say this is 0, and let's say that we have 0, let's say this is 1 bit period, another bit period, let's say we had another 0, so this is, let's say, 0 volts, right? And let's say we had a bit 1 over here, another bit 1. So in NRC we are going to go to 5 volts. So these are the bits. In addition to this, we have a clock signal. This is a clock signal at the center. Okay, so the clock signal is, let's say like this. Okay, so every cycle of the clock we are sending 1 bit, let's say. And what we are going to do is we are going to XOR these two. So what I mean is that if I have minus 5 volts, I'm going to think of it as being a 0 in both cases, and plus 5 volts is going to be a 1. So what is the resultant going to be? Okay, so I XOR these two. So I end up with a signal which looks like this. Okay, and it's going to be the same over here. Okay, so what I'm doing is this is 0 and this is 1, so I get 1 here, right? 0 and 0, so I get 0 over it, right? So I'm just XORing these and getting the result here. Now here I have a 1 and a 0, so I'm going to end up with 1. Here I have a 1 and 1, so I need to go back to 0. So it looks like this. Okay, so this is good in the sense that in every bit I have a transition. Okay, but unlike RZ, return to 0, I don't have 3 levels. I just have 2 levels, 2 voltage levels to deal with, okay, which is a good thing. And I don't really have a string of, even if I have a string of zeros or a string of ones, I don't have a constant signal. The signal is always changing. So I don't have to worry about baseline wander. I don't have to worry about clock recovery, because I will have these transitions every so often, right, which can help me do the clock recovery. Okay, so of course it's a little bit tricky. We'll have to build a circuit to do the clock recovery properly. But but you never have a long constant signal coming from the sender. So how do we detect what the bits are which are being sent? Okay, so suppose we know where the bit begins. So let's just say, so suppose I know the bit starts here. Now what I can do is I can say that here the transition was in the positive direction, which means it was a 0. Okay, and I know that the bit began over here. Okay, the signal for the bit began over here. Again, this is going positive also. Here it went this way. Okay, the transition was this way, so it's a 1. Transition was here, it is 1. Okay. So that's great. By looking at the direction of the transition in the middle of a bit, I know whether it was a 0 or a 1. But suppose I didn't know where the start of this bit was. Suppose I mistook this to be the start, what I am showing over here in the middle of the bit. Then things could go wrong. Okay, so if I think, for example, suppose I think that this is the start of the bit. Suppose the receiver mistook that as being the case. Then he would think that this is a 0 because the transition was upwards, positive. Okay, so this is going to be a problem. So I definitely need to know where the bits start if I'm going to use Manchester code. Also, I need to have the polarity correct. So I need to know what is plus and minus. So you're going to get, let's say, 2 wires from the sender, and you think that one, that you have to just look at the relative voltage between them. And if by mistake you flip it over, you may think that his plus 5 volts is actually minus 5 volts, and then you're going to get all the bits wrong. So we need to know for Manchester coding where bit starts, where a bit signal starts, and we need the correct polarity also. So the sender is sending you 2 wires, okay, and so maybe the relative voltage here is plus 5 volts, but you flip them around while measuring, and you will actually see, you think that this is his positive, right? But you will see minus 5 volts. So this has to be done correctly. Okay, but if you do it right, then we are good to go. So the question is, but how do you know when a bit signal is beginning or not? So you might think, oh, how is that possible? And that is done by something called a preamble. So a preamble is a known signal which helps the receiver synchronize in some way with the sender. So the preamble doesn't have any bit information, it's just a known signal which is sent out, and the receiver is going to look for this known signal and it's going to be able to synchronize with the sender. Let's talk a little bit about the preamble. So you have some signal information corresponding to your bits sent in this period of time, whatever it is, based on whatever line coding you're using. Let's say it's something like this, whatever, right? Based on the Manchester coding. So before this, you would have a special signal which is called the preamble. Which is fixed, which is known in advance. Right? So maybe there is nothing sent on the wire. Maybe the wire is just quiet, there is no signal at all. And let's say somebody needs to send out a packet. These are the bits in the packet. But before that, some known signal is sent out, whatever. And this helps the receiver synchronize with the sender. So it will know, for example, that the bits are going to begin here based on this signal. Okay, and by then already the receiver would have synchronized his clock, or he would have actually locked on to the clock of the sender based on this preamble. Right? So as soon as these bits come in, he's ready to go. He knows when they are beginning, he knows when to sample to see whether it's a 0 or a 1 and so on. Okay. So preamble, you can think of it as being some sort of a physical layer header. Right? These bits correspond to, will have MAC layer header, data link layer header, IP header and so on, TCP header, and then the actual application data and so on. You can think of this as being some sort of a physical layer header. So you have these sorts of preambles in wired systems, but also in wireless systems. So in wireless, of course, they have to do much more than just synchronizing clocks. They are used to detect the quality of the channel and so on. Okay, so this is a little bit about coding used. So we talked about NRZ, RZ, and Manchester coding. Okay. So there's couple of more things we need to discuss about wired before we go to wireless signaling, and one of them is differential Manchester coding. Okay, so what is differential Manchester coding is used in a technology called IEEE 802.5, which is used in these token ring LANs. Okay, so it's a local area network where token ring is a technology that's used in the DLL layer, okay, for medium access and things like that. Okay. So when we talk about medium access, we might touch upon this topic. Okay, but what is the coding done over here? So essentially, if you have a 0, then what is going to happen is that the first half of a bit is the opposite of the last half of the previous bit. So it will become clear what this means when I actually draw it out. So first half is opposite of last half of the previous bit. So we're talking about signals here. So when you consider the duration of a bit, the first half of this bit, the signal there, is the opposite of the last half. But when you have a 1, the first half is the same as the last half of the previous bit. So the differential Manchester coding signal would look like this. So let's say that we have bits 0, 0, 1, 1. Okay. And so it would look like this. Now I said if there is a 0 here, then the first half of the bit, that means this is the bit period. So in the first half, the signal level is going to be the opposite of the last half of the previous bit. So it's going to be the opposite of what we have here. So we will have a clock-like signal in every bit. Now we have a 1. So 1 in the first half of the bit, it is the same as the last half of the previous bit. Okay, so what should we do here? Well, we just reproduce the signal. Okay, it's the same as what we had here. So here it is the opposite. Here it is the same. Okay, and so we have a clock signal. But if we have a 0, if we have a 1, we make sure that the first half is going to be the same as the previous bit, right? The last half of the previous bit. So now again we have a 1 over here. So the first half should be the same. Okay, so this is the first half, it should be the same, and we have this, and we have another 1, so of course it's going to be the same. Okay. Okay, so it's somewhat similar to what we had in the Manchester coding, that we have a clock signal. So the signal level changes in every bit. That's what we wanted to get rid of the problems we had in NRZ. Okay, so the signal level changes in every bit, but at the same time, we don't have other issues that we have with Manchester encoding. We solve with the differential Manchester coding, which we have with Manchester encoding, is the need for polarity. Okay, so we saw here that if we don't have the correct polarity, we may mistake 1s for 0s and vice versa. Whereas let's see how we solved it in differential Manchester coding. Here we say that you have a 1 when we see a signal to be constant for 1 bit's duration. So clearly I could eyeball this and say that this is a 1. Here too I must have got a 1 bit coming because I have this long duration. Whereas here I could eyeball it and say that I had a 0. Okay. So even if I had flipped the signal upside down, I had got the polarity opposite, everything was flipped about this axis over here. I would still be able to recover the bits ones and zeros correctly, okay, just by using the same method. So we've clearly overcome the problem of polarity which we had with Manchester encoding. There's one more way we can get around the problems of NRZ besides actually putting in a clock signal like we had in Manchester or differential Manchester encoding, and that is by doing coding. So let's talk about the 4B, 5B coding. So recall with NRZ, if you had lots of zeros or lots of ones consecutive, the signal stayed constant. So that was gave problems for clock recovery and baseline wander and so on. So instead of actually putting in a clock signal, what we could do is we can actually change these bits. So what if I insert some ones over here, or what if I insert some zeros over here, just so that I don't have a long strings of ones and zeros. So what we can do is we can take the data bits and we send it through this coding scheme, and we get some coded bits, and these are actually sent out on the wire. Okay? So if we do this coding such that there are no long strings of zeros or ones, then we've pretty much solved our problem. So this 4B, 5B coding does just that. So we take all 2 to the power of 4 bit combinations, 4-bit combinations. I shouldn't say bits. I take 4 data bits, and what I'm going to spit out is 5 coded bits. So one example is if I have all zeros, what I spit out is 0, 1, 0, 1, 0. Okay, so this is what the coding gives me. Another example is if I have 1, 0, 0, 0. So there is a string of 3 ones here. I instead will transmit this. Okay, so this, of course, I have to look at all possible combinations, right? And you can find the full 4B, 5B encoding in your textbook. Okay. So this ensures that you don't have a string of more than 3 zeros in the transmitted bits. So it ensures that there's at most 3 consecutive zeros in the transmitted bit string. I should say the coded bit string. Okay, so suppose, for example, I had, these were my bits. These were the data bits. I will take 4 of them at a time, use this coding scheme to convert them. So I would have, what I would instead transmit is this. And there would be something like this and so on. Right, and I ensure that in this coded bit string I can look anywhere. I will never find more than 3 consecutive zeros in a row. Okay, so this is going to ensure that I don't have a very long string of zeros. Okay, but what is the disadvantage? Well, I'm not pushing through as much data as I could. Okay, so instead of pushing 4 bits, let's say in a particular amount of time, instead of sending 4 bits, instead of sending 5 data bits, I'm sending only 4 data bits, right? So just to clarify that, so every 5 bits that I'm transmitting corresponds to only 4 bits of data information. Okay, there's one redundant bit. So I'm losing a little bit on efficiency, but I'm getting rid of some of the problems of NRZ. Okay, so there's before we wrap up with line coding and wired systems and we look at wireless, there's another concept which we need to discuss, and that's the baud rate. So you might have heard of bit rate. So the bit rate that we transmit using any particular line coding and so on is the maximum number of bits that we are pushing through per second. Let's say transmitted per second. So the baud rate is a little bit different. So the baud rate is defined as the maximum number of distinct symbol changes made to the transmission medium per second. So it's the maximum number of distinct symbols or let's say symbol changes made to the transmission medium per second. Okay, so let's look at an example and we'll see where exactly this baud rate comes into the picture. So let's say that we have a Manchester encoded signal. So we have 0. So we're sending this out. So this is the bit duration. Another 0. Okay, so this is the 0 level. And let's say there was a 1 over here. Okay. So here, how many times are we how many times are we changing the symbols per second? That's what we need to figure out. So this is considered one symbol. So each level we are considering as one symbol in this particular case. So we are sending 2 symbols over here. Okay, and let's say that this duration of a bit is, let's say, 0.1 microsecond. So what is the bit rate? So we are sending 1 data bit per 0.1 microsecond. So the bit rate corresponds to 10 megabit per second. Okay, that's just 1 over 0.1 10 to the power of minus 6, right? What about the baud rate? So we are changing this symbol in the worst case, sort of in the maximum case, we are changing it every 0.5 or 0.05 microseconds. So the baud rate is 1 over 0.05 microseconds, which is 20 million symbols per second. Okay, so why are we interested in both of these things? So clearly the bit rate is important from an application point of view. How much of information can I push through? Baud rate is measuring how efficiently I am using that particular wire. Okay, so why do we talk about it? Well, because if I look at it in the frequency domain, just like we had looked at for I had looked at attenuation and so on, right? When we looked at attenuation, we looked at frequency, and we said that the attenuation goes up typically in a wire, right, for twisted pair and so. So pretty much only a small part of it is usable. So I would say this is of course is a very loosely used term, because you can in theory use the whole spectrum, right? You can send very high frequencies over any wire, but the attenuation becomes too much and it doesn't make sense to use very high frequencies, let's say on a twisted pair, right? So if the attenuation is too much, let's say this much, just too much, let's say I put a threshold here. So I will say that this is the unusable part. So there is only this much frequencies that I can send through. Whatever signal I send on the wire can only occupy a certain range of frequencies. Okay, and the question is, given this limit, whatever this is for a particular wire, how much of information can I push through? Okay. So the frequency content of a signal is related to the baud rate. So frequency range of a signal on a wire is related to the baud rate. And so suppose I am given a time domain signal. Okay, this is time, and suppose I want to look at the frequency content of this signal. How do I do that? Well, you may be familiar with Fourier transforms. So I just take the Fourier transform and I go from the time domain to the frequency domain. Okay, so this is the time domain signal, and let's say this is, let's not call it f of t, let's call it g of t, and let's call this g of f. Okay, so let's say that the Fourier transform looks something like this of any particular signal, right? So if I make lots of transitions in the signal over here, right? So this is the actual signal that I am transmitting. I mean, I don't care about what bits are there. This is the signal that I am transmitting. And if I take the Fourier transform of this signal, it's going to look maybe something like this. And this has to fit in over here. Let me just call this some f0. this had better fit in here within the usable part of this frequency, because otherwise it's going to get distorted. If too much of the frequency content in the signal is beyond f0, it gets distorted, right? So baud rate is sort of, you want to make your baud rate something close to this f0. Okay, that's sort of the maximum baud rate that you can have on the signal. And at the same time, for whatever I send on the channel, I want the bit rate to be as high as possible. Okay, so because of, in Manchester encoding, we have put this clock signal. Okay, so we are ensuring that there is a transition every time in every bit. We get a higher baud rate than a bit rate. Whereas if you look at NRZ encoding, the bit rate and the baud rate are going to be the same. Okay, so I leave that as an exercise, but just to be clear, bit rate and baud rate are going to be the same when you use NRZ encoding. Right? Whereas in Manchester encoding, because we've introduced this clock which changes twice as fast as the bits, okay, there we've sort of got a baud rate which is twice the bit rate. Okay? So ideally you want these to be as close as possible, right, given all the constraints that you have.